Alright, let's get started. Well, good afternoon, everybody. This is Arun Thiraviam, and I am a simulation specialist at GoEngineer. Today, thank you for joining us on our GoEngineer simulation webinar. So today I'm going to talk a little bit about simulation without constraints, an aspect of structural simulation that all of us battle with on a daily basis that we haven't acknowledged. So I'm going to try and present a concept with our structural simulation tool in SOLIDWORKS to kind of demystify certain problems that you deal with uh, on a daily basis while running finite element analysis and kind of figure out ways to overcome these problems. So here's a video of a balloon on a beaker that has water or some sort of a liquid that's being heated. Now what's essentially driving the expansion of the balloon is the air pressure or the liquid pressure that's built inside the beaker that applies an equal pressure on all the walls because liquids and fluids and gases and liquids have the tendency to fill up a container and apply equal pressure to all the walls. But what's preventing the beaker from essentially moving? So here's a schematic that actually explains what's going on here. So you have uh, the beaker that has a constant cross section that's essentially revolved around a center line, and you have a uniform pressure by virtue of the expansion of the water and the air inside the beaker applied to the walls of the beaker. Well, what does this mean for structural analysis? Well, we deal with these sort of problems on a daily basis. How is this thing constrained? Now, what is preventing the beaker from, flying out in any specific direction? Is because the magnitude of the pressure isn't high enough, and even if the magnitude of the pressure was high enough, there isn't an imbalance due to the uniformity of the pressure distribution around the center line. Now, with respect to this uniform distribution, there's no way by which the beaker is essentially held. So we call the system a self-equilibrated system. So by which the system does not have any external constraints, but the constraints is only by virtue of the pressures acting on the walls of the system, not creating an imbalance. Now, how I'm going to illustrate this fact is through validating and optimizing this pressure vessel you see here. Now, this pressure, it's a really simple pressure vessel with hemispherical caps. Now, what I'm going to attempt to do is essentially create an internal pressure on the wall of the vessel using SolidWorks simulation and essentially study the uniform expansion of the pressure vessel and essentially validate the expansion that I see with the software with a few hand calculations. Now, I'm going to use this example as a method by which we use non-conventional constraints to essentially simulate these self-equilibrated assemblies that don't have any constraints. Now, as far as the setup goes, now we've established that we're going to apply uniform pressures to the walls of the pressure vessel. But what about the constraints? So let's talk about the constraints for a second. While the pressure vessel isn't supposed to shoot off in any specific direction, we need to facilitate the expansion of the pressure vessel by the uniform pressure. So if we actually think about it, now the pressure vessel should not be allowed to rotate about its axis or move along its axis. It's only allowed to expand about its own axis. It's essentially a giant metallic balloon. Now, if you come to think about it, now how are we going to fixture these things in order to avoid these stress artifacts that come up that usually lead to embarrassing situations when you present your designs to management and they're like, hey, what is that? What is that artifact we see there? Is that a point of failure? So essentially, what we're going to figure out is how do we simulate such a case when there virtually seems to be absolutely no constraints that's holding the pressure vessel in place without compromising its expansion. Now let's jump into the software. Here's my little pressure vessel design. That's a cross-section view, just giving you an idea of what the internal walls look like. Now, in order to structurally analyze the pressure vessel, what I'm about to do is I'm about to add in the SolidWorks simulation package through the add-ins tab. Now, once I hit the add-ins tab and I hit the SolidWorks simulation button, a couple of things happened. Now, this command manager updates to have the simulation tab. Now, getting into the simulation tab, what I'm about to do is set up a new structural study. So, hitting the new study button gives me access to a buffet of studies that I can essentially run run different flavors of simulation in on this model in order to virtually test the model. But what I'm going to run is a simple linear static analysis. So hitting the green checkbox, the feature manager tree updates to include all the elements in order to set up a simulation. Now, just going down the tree, making different assignments, I'm going to give this pressure vessel a carbon steel material from our database. Now, as far as applying the external loads on the internal walls of the vessel go, it becomes a little convenient grabbing the section view. So when you grab the internal walls, all the uh, all the entire circumference of the walls are selected. So I'm going to right click external loads, grab pressures, and I'm going to grab these three surfaces. I'm going to apply a 10 megapascal pressure. Now, if I did manage to constrain this thing at, say, the base, you're going to have anomalous results that may not be necessarily right, because like I said, now the goal here is essentially to enable the pressure vessel to expand without actually having it to exhibit any rigid body motion. You essentially don't want it to shoot out in any specific direction. So what I'm about to do is I'm about to delete this fixture that I created and create reference geometry fixtures. Now what reference geometry fixtures are is that I can control how the model moves or how the model does not move using the features on the model and using the coordinate system that you see here to control each individual degrees of freedom. Now grabbing the advanced fixture button gives me access to something called the use reference geometry fixture. Now, with respect to the pressure vessel, I know for a fact that I don't want this to rotate about its axis. Now, in order to apply those constraints, I'm going to grab the two circle features, and in order to control the rotation, I'm going to use an axis that I defined while modeling the pressure vessel in order to control the degrees of freedom in cylindrical coordinates. So as soon as I grab the axis as the reference, now the degree of freedom control changes to reflect changes from the Cartesian coordinate system to the cylindrical coordinate system. So I have radial, circumferential, and axial degrees of control. So I know for a fact that I wouldn't want the pressure vessel to rotate about its axis. Now the only other constraint that I need this to have is preventing the vessel from shooting off in the x direction. But if I constrain both these edges again in the x direction, it's going to prevent the pressure vessel from expanding like a balloon. So what is the workaround here? So in order to have a completely constrained model, you grab the advanced fixtures again, you grab one of the edges, use the axis, and control just the axial motion of the pressure vessel on one edge. So this way the pressure vessel is allowed to expand in the x but not allowed to move along the x or in the axial direction. Now once I have the material properties, the fixtures, and the pressure in, all I need to do is run the analysis. Now on running the analysis, I have a von Mises stress distribution that indicates that my pressure vessel is under yield strength. But anytime you take pressure vessel analysis, it's the resultant stresses are usually meaningless. What you'd like to study are the hoop stresses or the circumferential stresses in the cylindrical coordinate system. So in order to get the hoop stresses on the pressure vessel, what you do is you edit your plot, you switch the plot to SY, and then you grab the axis for the cylindrical feature that you're trying to study the hoop stresses for. And finally, um, you hit the green check mark. Now on hitting the green check mark, a couple of things happen. The first thing is on the bottom right hand corner of your screen, you have a coordinate system, a little icon indicating that you shifted to the cylindrical coordinate system. And using the Y normal stresses indicates that you're actually viewing the hoop stresses. Now, if you wanted to see the axial stresses or if you wanted to see the radial stresses, you will need to switch the Y normal stress to an X or Z. X corresponding to the radial stress and Z corresponding to the axial stress. So let's just keep it as the hoop stress because the hoop stress is usually the greatest stress that a pressure vessel experiences of all the principal stresses that essentially govern its expansion. Okay, great. Now this is one way of doing running this analysis in order to study the pressure vessel expansion, but how can I simplify this analysis? How can I make these constraints a little more intuitive? Uh, so I have another proposition. In order to simplify the analysis, what I have set up is another model that is essentially half the vessel. Now I notice that the vessel is symmetric about multiple axes, so I'm just going to utilize its symmetricity about, say, the XY plane in order to set up the second analysis. Now, once I use my configuration manager to switch to the half symmetric configuration, I'm going to set up a new study pertaining to this specific configuration. Now, in the same manner as I set up my previous analysis, I'm going to use a plain carbon steel material. Now I'm going to apply a uniform pressure of 10 megapascals on the inside of the pressure vessel. Now here come the constraints. Now we know for a fact that the pressure vessel is symmetric about this axis. Now in order to establish the symmetricity, what I can use is another fixture. So if I right click fixtures and I hit advanced fixtures, I have the symmetry fixture that I can apply to every face of the pressure vessel that essentially specifies your plane of symmetry. So now selecting this face brings up a preview that virtually completes the pressure vessel, but the analysis is actually only being run on half the vessel. So this about saves half your simulation time. You know, uh, gives fostering confidence in going to more complicated analyses and more complicated boundary conditions. Now, what does a symmetry boundary condition do? It essentially prevents the pressure vessel from moving into the XY plane. So that will automatically constrain the pressure vessel from its circumferential rotation. So all you need to do in order to completely constrain this model without constraining this model is to add another fixture to control the axial motion, just like we did in the previous example for the entire pressure vessel. So I'm going to grab the edge, I'm going to grab the axis, and I'm going to click the axial constraint button in order to prevent the pressure vessel from shooting out in the X. Now with that constraint in place, now for added stability, I'm going to add the circumferential constraint. So anytime you run an analysis, now the first indicator that your that your model does not have adequate fixtures is essentially through this error message. So this indicates that you will need to add another constraint, that the symmetry constraint wasn't sufficient in order to prevent the circumferential rotation of the vessel. So let's add those constraints. So I'm going to go into the fixtures again. I'm going to use the axis and I'm going to control the circumferential rotation. And there you have it. Now again, looking at the hoop stresses, you'll notice that the hoop stress is similar to what I got in the previous analysis, around 150 megapascals. Now let's kind of analyze what went wrong while utilizing the symmetry fixture. Now while utilizing the symmetry fixture, although I managed to prevent the pressure vessel from rotating or moving into the plane or along the Z direction, I did not prevent the pressure vessel from moving along the Y direction. So with the symmetry constraint, with the half symmetry, I only constrain one axis or one coordinate of motion. I essentially have two coordinates that are still free that require additional constraints. So this wasn't totally different from our previous analysis. The only uh, the only difference was essentially the additional symmetry constraint that you needed to add, and well, you save half the model. You save meshing half the model. Now, if you want to look at the entire model as well, you can display symmetric results to mime the calculations. So in the same fashion, what I've done is I've set up a quarter symmetry model. Now with the quarter symmetry model, the constraints become a little more, a little less intuitive, but a little more complete. So now I've set up a static study, applied a material property. I'm going to apply um, symmetry fixtures again. We'll right click fixtures, head into advanced fixtures, grab symmetry. Now this time the symmetry application will be on two faces. Now this symmetry fixture is going to prevent the circumferential rotation of the vessel, because not only are you blocking it from moving along the Z, you're also preventing it from moving along the Y. So the only other constraint you'll need to add along with the symmetry fixture is just the axial fixture. I'm going to add the internal pressure of 10 megapascals. And I'm going to run the analysis. And there you have it. Again, looking at the hoop stresses, we have about 150 megapascals again. Now, what I did was I took this analysis to another level and actually used a quarter half symmetric model, as I like to call it. Now I'm going to an analysis that I've already set up. Now in the quarter half symmetric model, what I've noticed is the pressure vessel has an additional plane of symmetry. So my symmetry fixture is not only restricted to the two sides, but it's also applied to the symmetric face about the YZ plane. So this way, the pressure vessel is constrained from moving in all three coordinate directions. The only way it can really move is away from this symmetric, preview, which features only the expansion of the pressure vessel. So we've reduced about three constraints to just one. So rerunning the analysis gives you about 150 megapascals along the hoop again. And of course, if you wanted to look at the symmetric results look to view the behavior of the entire model, there you have it. Now, how can we further simplify this analysis? Now, the only other way we can simplify this analysis is you'll notice that this entire geometry could be created by just revolving a cross section. So we can actually simplify this three-dimensional analysis to 2D analysis. So I want to quickly show you how I set up a two-dimensional analysis that grabs only the cross section that was used to generate this pressure vessel to run the analysis. So as soon as you hit the static study, you hit use 2D simplification. Now the only thing you need to decide is, was this an extruded object or was this a revolved object? Now since this was a revolved object, it's axis symmetric. Now let's grab a section plane that you would have used for the revolve, and let's grab the axis of symmetry. Now grabbing those two essentially generates a preview, a two-dimensional preview of the section that you're going to run the analysis on. Now once you have the two-dimensional preview, all you would do is assign a material property, assign the boundary conditions, 10 megapascals. Now what about the constraints? Now all we've attempted to do in our previous three simulations is prevent the axial motion, but here you don't have the liberty of selecting any specific point in order to control the axial motion. So what you can do is actually prevent the axial motion by just selecting one point. Now this way, on selecting the point and selecting the direction of the constraint, which is in the x direction. Now this is going to prevent that point from moving along the x direction, hence preventing the entire vessel from moving in the x direction. So this way you don't over constrain the model and you prevent looking at stress artifacts that could ruin your design. You can see that the two-dimensional analysis runs relatively quick also. And if you wanted to look at a 3D plot where it essentially revolves the result around the axis of symmetry. Jump. Now to quickly summarize our analysis, what we did was we ran the analysis across about 6 models. Now I did not demonstrate the 36-degree slice, but you would imagine the 36-degree slice would also involve applying a symmetry constraint and rerunning the analysis. Now you'll notice that each of these models have similar hoop stresses. Now how can you validate the results of your analysis? Now, since this is a really simple model, we have simple hand calculations by which we can validate the hoop stresses, the maximum stresses that a pressure vessel experiences in its expansion. And now we can see from the slide that the hoop stress is around 150 to 158 megapascals. Now, here's the formula for the hoop stress. Sigma theta equals internal pressure times the radius of the cylinder over the wall thickness. Now, since both of these quantities are since the internal pressure is 10 megapascals, the radius of the cylinder 150, and the wall thickness 10 millimeters, this gives us about 150 megapascals, which kind of correlates with the result we see from the analysis, indicating that this was an accurate representation of what you'd see for a big metallic balloon. Now I have one more example that kind of illustrates this this unconstrained constraints, if you will, which is a three-point bend test. Now, what's so peculiar about three-point bend test? Essentially, three-point bend tests are used to study the flexural response of materials. Now, here we have a simply supported specimen. Now, as far as simply supported specimen go, we know for a fact that the specimen is allowed to move in all directions, save for the direction of the loading. So what we're going to do here is we're going to try and simulate the scenario in SOLIDWORKS and validate these results with the hand calculations. Now, what's so tough about this problem is that, okay, we have a force over there that essentially mimics the force of the actuator. Now, what about the constraints? Now, we have a simply supported constraint over there, indicated by the green arrows. Now, the salient feature of this constraint is that it needs to enable both the expansion and the motion of the pressure vessel. I meant of the, I apologize, of the specimen about the simply supported fixture, and by virtue of the Poisson's effect, you need to let this contract and expand based on the different bending stresses that the specimen experiences. So that's a little bit about the setup. Now I'm going to jump back into SolidWorks to show you how I've run the simulation on this. I'm going to open up my three-point bend test example. So typically how you'd approach the three-point bend test is this way. So you'd essentially grab the simulation add-in, you hit new study, grab the static analysis tool, apply a material property. Now I've created a custom material property for this specific example because I wanted it to correlate with the hand calculation. So I had a custom elastic modulus of about 78.15 megapascals. So I'm going to apply that material type. Now the only other things I need to apply are the forces. Essentially the force is going to be along that line. Now I need the force to be normal to the line. So I'm going to grab a face and I'm going to grab everything that's normal to the face, reverse the direction, apply a 15 Newton force, and there you have it. Now with respect to the constraints, now there are multiple ways you can apply the constraint. Now the first thing that you'll think of doing is essentially grabbing a fixed geometry and enabling the specimen to pivot about the fixed geometry. But what you essentially miss out here is that while you're enabling this to pivot, you're preventing the specimen from moving along the x direction that could add an additional level of stiffness to the way your component is deforming. So on running this analysis, as far as the displacement results go, now the actual displacement from the Ingstrom, the machine that was used to run the three-point test with these conditions, is 2.4 millimeters. But what you're seeing here, due to the additional level of the additional level of stiffness due to the constraints along the x direction, is that it's much lesser. Now, in order to accurately run this simulation, let's duplicate this analysis and revisit our fixtures. Now, let's leave one of the edges fixed. Now, in order to allow the x motion, the x direction of motion, but still prevent the specimen from moving in the the y and the z direction, let's use reference geometry fixtures. So I have the edge selected. Now under my reference geometry fixture, I'm going to select a plane. And a little word of advice: if you grab the front plane for the reference geometry, now these usually align to the global coordinate system, so it's easier to understand what each of those icons do without looking at the previews. Now essentially what I'm trying to do here is constrain this about the Z. So I'm going to grab the Z and then constrain this about the Y's to enable the pivot. Now I'm going to leave the X free so that this is able to, this is so that you accurately represent a simply supported situation. Now on running this analysis, the famous excessive displacements dialog box. This indicates that the model is deforming excessively that might influence the stiffness of the model. So you need to get simulation to use a solver that keeps track of the stiffness of the model and updates the stiffness as your model is deforming. So let's use the large displacement solver that's built into the static solver for now. So you can see that it changes from the one-step process to a multi-step process, where in each step it's updating the stiffness as your specimen is deforming. Now you notice the displacements have gone up, and this would be an more accurate representation of what you actually see on the Ingstrom. Previously, the displacements were just 1.5 millimeters with both of these constraint prevented from moving along the X. Now, after on the application of or on freeing up the X degree of freedom, that's added an additional level of flexibility, giving you more accurate results. Now, how you can also push this analysis to the next level is by actually breaking this down into its component for breaking this down into using split lines. Now, starting up a new study. Now, to set up this model, what I've done is I've broken the model into two halves. So I can essentially exclude one of the halves from the analysis, and I can apply a symmetry because essentially this is a symmetric deformation. Now I'm going to apply a custom material here. Now after the custom material, the fixtures become relatively straightforward. Now we know for a fact there's a symmetry fixture here that's going to prevent the X motion of that face. Now the only other fixtures I need to add are reference geometry fixtures about these edges. Now why I'm selecting these edges is that you know for a fact that during the bending process, you're going to have uniform expansion or contraction along the Z by virtue of the bend, and it's going to be uniform about that plane or about all of these splits. So I'm going to grab those splits, I'm going to grab the front plane, and I'm going to prevent the out of plane deformation of just that face, or I mean of just the edges. Now the only other thing that I need to add is essentially reference geometry fixtures here that pivot, that enable the system to pivot about the constraint points. Grabbing the front plane. Okay, and let's not forget the load. Now since we have half the model, the load becomes half as well. So we have a total load of 25 newtons in the y direction. Yeah. Yes, for excessive displacement. Okay, great. Now the displacement again vibes with what we got with the full model. Now, if you essentially want to see just the bending stress, now let's switch away from the von Mises to the SX component, indicating the stresses along this direction, or the global X direction. Now we have a maximum stress of 3.71 megapascals. Now let's jump back into the software and kind of validate that with hand calculation. So I've run the simulation on the full and the half model, and I get 3.7 megapascals. Now in order to run the validation, we have our usual bending moment or bending stress formula. That's essentially the moment times the distance from the neutral axis over the second moment of inertia. Now running all these calculations, gives me 3.75 megapascals. And I'll leave this slide on so you can absorb the calculation. Now we have 3.75 megapascals from the hand calcs. We have about 3.66 with the probe tool with uh, um, at the at the outer fibers. Now, as a quick summary, now what we try to look at here in the analysis is that we can all agree that that in order to run a successful finite element analysis, you need completely constrained models, or you're going to see this big old error message that's essentially going to indicate that your model is shooting off. It's exhibiting some rigid body motion in one of the coordinate directions. Now, in order to simulate self-equilibriated models that don't really have constraints, you essentially utilize symmetry, roller fixtures, and fixtures driven by reference geometry to essentially control every degree of freedom. For instance, in the pressure vessel case, we managed to control the axial and the circumferential degrees of freedom, permitting the radial expansion of the vessel. Now, while constraining the assemblies also, you tend to use as minimal features as you can, as the smallest features that you can, for instance, vertices and edges, in order to prevent the rigid body motion, and secondly, to avoid over constraining your models. So I hope you found the two examples useful to conquer these self equilibriated assemblies. To finish off, what I also have is I've run an optimization analysis where I wanted to optimize the wall thickness of the pressure vessel and the radius of the pressure vessel in order to maintain its strength whilst minimizing mass. Now, just a little glimpse of that experiment. Now, how I executed this was using the design study tool. Now, the only thing that the design study tool needs are the parameters that govern your or drive your geometry, and the range that you'd like to vary these parameters. You can add as many design parameters as you want by just simply selecting a mod dimension that you can access on the screen. So I can even access the 360 degree sweep and give it a variable that I can use in order to change and parametrically study my model. Now after I've inputted the parameters that I'm varying, now what I need to specify is a constraint. What am I designing for? Now I essentially want the stress distribution of my pressure vessel to be below 200 megapascals. And finally, what's my goal? Whilst maintaining this constraint is my goal is primarily to minimize the mass. Now on hitting the run button, what happens is the simulation solver populates a set of iterations that sweeps the geometry through the range you've specified and essentially gives you the optimal configuration. Now, the benefit of this analysis is you can go through each of these configurations and also look at the stress distribution by virtue of these configurations. So this is the stress distribution in the optimal system, while this is your stress distribution in your initial system. So essentially the tools that we use to leverage, today to run the analysis feature in all levels of our SolidWorks simulation package. So the SolidWorks simulation tool comes in 3 tiers. There's a standard tier, there's a professional tier, and a premium tier. While the standard tier gives you access to linear static analyses, the professional tier gives you the optimization tool and the 2D simplification like the one we ran in the pressure vessel. Now, why I highlighted the nonlinear analysis was in the 3-point bend test. Anytime you have a large displacement analysis, you're recommended to use the nonlinear solver because it keeps track of the stiffness of the model as the model deforms, and you can also input stress strain curves that model metal plasticity to study post-heat behavior of metals and plastics, and also lets you simulate nonlinear material like rubber. Well, that concludes my presentation. Please visit our GoEngineer website. This is where you can get access to my webinar and many other webinars by a talented group of engineers here at Go. And this is Arun Thiraviam. Thank you so much.